In this video, we're continuing our discussion of numerical differentiation. And in particular, we're going to talk about finite difference approximations of mixed partial derivatives. Now let's consider a two-dimensional problem discretized in x and y as shown here. And suppose we want a numerical scheme to determine the mixed partial derivative, partial by partial x of partial f by partial y. So in all of the previous sections, we have just talked about developing finite difference schemes in a single direction, but here we can extend this to look at partial derivatives when the domain is discretized in more than one direction. So here I denotes the grid points in x and j denotes the grid points in y, and we want to determine this mixed partial derivative at our point xi, y, j. So let's use a central finite difference formula to discretize the first derivative in both directions. So we're first going to start with the x direction. So we're going to replace this derivative, partial by partial x, with its centered finite difference approximation. So the centered finite difference approximation is 1 over 2 delta x, where delta x is our spacing between grid points, and here we're assuming a uniform spacing, with delta x being our spacing in our x direction. And then we evaluate this part at the point I plus 1. So if we want to know the derivative at this point, we want to evaluate at the point I plus 1 minus the point I minus 1, and then again divide by the 2 delta x. So this is all the centered finite difference approximation for this partial by partial x. And we know that this formula is second order accurate in our delta x spacing. Then we can apply this again to replace these derivatives, the partial f by partial y, by the centered finite difference approximation in the y direction. So here what we've done is take this partial derivative becomes 1 over 2 delta y, because delta y is our spacing in the y direction. And then we're evaluating, so this point, we were out here at I plus 1. So for this point, we're going to evaluate that at the one above it, so j plus 1, minus the one below it, j minus 1. And then for this derivative, becomes here, we're going to evaluate, at this point, we're going to evaluate the one above it, so I minus 1, j plus 1, minus I minus 1, j minus 1, and then divide by 2 delta y again. And here we've replaced the order of accuracy with the two grid spacings. So delta, it's second order accurate in the delta x and second order accurate in the delta y. So then this becomes our approximation for this mixed partial derivative using the centered finite difference scheme. And we can extend this using any of the techniques that we've talked about, or the finite difference approximations that we've talked about. So for example, if we'd use the forward finite difference in both the x and y directions, use the forward finite difference in the x direction, but the backward finite difference in the y direction. So there's lots of different ways that we can do this, and we get different kind of combinations of using the different forward, backward, and centered finite difference schemes gives us these different methods to calculate the mixed partial derivatives.